Momentum. Momentum is another way of looking at motion. Now, before we looked at force and saw how it applied to mass times acceleration. Now we're going to take a look at force and see how it affects the momentum. Now, the easiest way to think about momentum is it's a measure of inertia combined with motion. So really what it is like our velocity vector, it is a vector, it does have direction, and like our mass, which is a scalar, it does depend on the number of kilograms a particular object has. But it really combines the two. It combines inertia, which is measured by mass. It combines the idea of how much you're moving, velocity, together. And really, one way of looking at momentum is the product of mass times velocity. It's really how difficult it would be to bring something to rest. So momentum is mass times velocity. It's pretty apparent why we can't use m again. We've already used m for mass. So we go to another letter, p. There's really no way of connecting it with the word momentum, but that's what we use. And again, you can see momentum is a vector, velocity is a vector. They both point in the same direction. Mass is your scalar, so the more mass you have for a given velocity, obviously the more momentum you have also. So momentum, a scalar, momentum, a vector, mass, a scalar, velocity, a scalar. Now, in terms of the units for momentum, momentum being the product of mass and velocity, it's fairly easy to see that with mass you have kilograms, and with velocity you have meters per second. What's not obvious is if you look at kilograms times meters per second, okay, and you change kilograms meters per second to kilograms meters per second squared, you have newtons. To do that, you've got to bring in seconds outside of that because you're putting another seconds in the denominator. That leaves us with newton seconds, and that's going to be very important for impulse, which is the change in momentum. So momentum you can either write as kilograms meters per second for SI or newtons times seconds. Again, here's the derivation of how we get to newton seconds. Here's for our original mass times velocity, kilograms times meters per second. Okay? We divide the denominator, we multiply the denominator by seconds. We also do that with the numerator. We bring the seconds outside. And again, here's your newtons, okay? Here's your seconds. So again, either or will work in this particular case. Again, if you don't remember the units for newtons, F equals ma, 1 newton is a kilogram meters per second squared. And again, by putting seconds on this side, it just balances the two sides. Dimensional analysis holds right here. Okay, other momentum units. In the CGS system, we have grams centimeters per second, or erg times seconds. Ergs are, as you might guess, force. Kilograms times kilometers per hour. That's really kind of sketchy as a unit because it combines hours with, basically other metric units, where we normally have seconds in there someplace. And then the British units, of course, are pound seconds. Just a quick way of demonstrating calculating the magnitude of momentum. A person with a mass of 80 kilograms walking briskly at a speed of 1.5 meters per second would have a momentum of 120 kilograms meters per second, or 120 newtons times seconds. Going much faster, an elite sprinter, mass of 60 kilograms, traveling at 10 meters per second, that's really elite speed, would have a momentum of 600 kilograms times meters per second. So momentum is proportional to the magnitude of the momentum is proportional to your speed. Here, consider a fairly large former football player, Jerome Bettis. His mass was 120 kilograms, so he was a fairly massive fullback. Let's say he ran a 6 meter per second speed. His momentum would be 720 kilograms times meters per second. And as a fullback, as a running back, you want to be as difficult as possible in order to bring down, and that can be achieved very easily if you have a lot of mass and you can get going quite a bit. Of course, being able to accelerate with all that mass is also a great advantage that he had too. Aroldis Chapman threw the fastest pitch ever at 105 miles per hour. There have been unofficial clock speeds in other cases. But considering the mass of a baseball at 0.145 kilograms, 145 grams, what would the momentum be? Now here we're taking a very low mass object and we're multiplying it by a fairly good velocity. Small mass, high velocity, and we see that this momentum really doesn't compare to the momentum that a person would have at a much lower speed. 6.82 kilogram meters per second, or 6.82 newtons seconds. And again, when you compare it to a human being who typically has a momentum in the hundreds, the baseball itself doesn't have a lot of momentum to it. However, you don't want to get hit by a 105 mile an hour fastball, because all that momentum is going to concentrate a force in a very small place, and you can get injured very badly. Now, momentum again is a product of the mass times the velocity, okay? And it's important to understand the momentum, but the most exciting examples happen when we change the momentum, and we do this using a force. Now, the change in momentum, we use a symbol delta for change. The change in momentum is equal to the final momentum minus the initial momentum, and if the mass doesn't change, which is pretty much the case for almost everything, the change in momentum becomes the mass times the change in velocity. Okay? Of course, we're looking at just the magnitude here. There's no vector part of this. We're sort of ignoring the vector nature. The place where the mass actually changes quite a bit is something we're going to talk about later on, and that's with the rocket. All right, let's do another example. Here we have that fastball being pitched. 0.145 kilograms, 95 mile an hour fastball coming at the batter at 42.5 meters per second. The ball is hit by the batter and travels directly past the pitcher with a speed of 108 miles per hour, 48.2 meters per second. What is the change in momentum? This is a tricky case because you would think, oh, well, here's my final value. I'll just subtract it by my initial. That's not how you handle this, okay? These two are going in two different directions, equal and opposite. Remember, when you have two vectors and they're pointing in opposite directions, one has to be the negative of the other. So when we calculate the change in momentum, we say the pitch coming in has negative 42.5 meters per second velocity. The pitch going out has positive 48.2 meters per second velocity. When we take the difference between these two, the difference between this, okay, there's the pitch coming in with negative 6.16 kilograms meters per second. Don't worry about the negative sign, because the negative sign really represents a direction toward the batter. The batter hits it out, it's almost 7 kilograms meters per second. We subtract this by this. Anytime you subtract by a negative number, you get an even larger number. And the change in momentum there is 13.2 kilograms meters per second. So the force from that bat is doing something to the momentum. It's changing the momentum by 13.2, okay, Newton seconds. So we will see one way to manipulate, one way to change momentum is to apply a force. An object in motion will tend to stay in motion unless acted on by a force, okay? The only way we can change the momentum is to change the motion. That requires a force. That's where this discussion of impulse comes into play. Impulse is simply change in momentum, okay? Remember this little symbol here? Here it is. Delta P, that's your impulse, okay? Impulse is how much your momentum changes. Now the impulse is created by the application of some force, okay? Right here, player's being tackled. Unfortunately, he's getting a shoulder to the side of the head. So I think he's been knocked unconscious because there's a football leaving his possession. But again, the greater the force and the longer the force is applied, newtons times seconds, the greater the impulse. Think about the units. The units of impulse are Newton seconds. The units of momentum are Newton seconds. The more newtons you can put on for more seconds, the greater the impulse. Now, yeah, and again, impulse is not just a factor of force. You can have a very small impulse from a very quick force, but impulse is how long you can apply a force and how great that force is. This is a strongman competition where this person's actually towing a crane, and to apply an impulse here, not only is he applying a lot of force, but he's doing it over a long period of time pulling on this rope. So again, the equation for impulse, all right, is how much force we put on times how much time goes by. That's impulse. So for instance, let's do this with a car. A car has a mass of 1,500 kilograms, okay? It's traveling 15 meters per second. We want to reach a speed of 25 meters per second to enter the roadway, to enter the highway, okay? It's roughly 25 meters per second, it's about 60 miles per hour, 55 miles per hour. How much impulse do we need to achieve this? Well, I take the mass of the car times the initial velocity, the mass of the car times the final velocity. Oh, here's the initial velocity, the final velocity. I take this minus this, that's final momentum minus initial momentum, that's change in momentum. Final minus initial will always give us change. And it tells us that we need an impulse of 15,000 Newton seconds to get that car from a speed of about 33 miles per hour to a speed of 55 miles per hour. Notice I can do this a number of two ways. Well, I can do this a number of ways, many, many ways. I can apply a very small force, maybe a net force of 250 newtons. This, by the way, is the total force because friction is opposing this. So if I took my foot off the pedal, I'd actually slow down. But with only 250 newtons of force, it would take me 60 seconds to reach 15,000. 250 times 60 is 15,000. If I triple the force, as you might expect, it would take me 1/3 the time to get that impulse. All right? Increase the force even more to 3,000 newtons, and now it only takes 5 seconds to get there. Increasing even more, now we're down to 2 seconds at 7,500 newtons, and our maximum, this would be a high-performance sports car, would probably be able to get me to 15,000 newtons in 1 second. And also notice the different accelerations. The best car could really accelerate, high-performance tires, high-performance car, it's about 10 meters per second squared. Impulse, again, is how much momentum we change. When a boxer throws a punch, what they're trying to do is maximize the velocity, okay, and deliver the largest impulse. They want as much force as possible, but to have it make contact in the shortest amount of time. That's why the worst thing you can do is step into a punch, because when you step into a punch, you have the momentum of your head and the momentum of the glove coming in, and the interaction time is the shortest. If you can move away from the blow, that reduces the amount of force because it decreases the delivery, it increases the delivery time. So again, force of impact is the impulse, how much you change the momentum of something, times the time. If you lean into a punch, you can very quickly get snapped back. If you move back with a punch in boxing, you can actually absorb some of the energy, and what that does is it greatly reduces the force, and it's really the force that does the injury. In martial arts, most of the blows that are used against rigid materials for demonstration, brittle materials, because with a very rapid force, we can break these materials. Again, these people are trained, and what most people don't realize is as you train to do this, you actually increase the calcification in your bones by doing repeated blows. Not only will an untrained person not make contact with this correctly, but without the bones being properly strengthened. Muay Thai, they do that with the shins. You're going to break your hand more than you're going to break any boards or cement blocks. So graphing force is a function of time. The impulse actually is the area underneath the graph. Unfortunately for this graph, the force turns on and the force turns off. that's not really a realistic representation of what's going on. A more realistic representation looks like this, where the objects make contact, begin to deform, and then move away from one another after they rebound, and then it goes down to zero. So in looking at real interactions, we can think about how these interactions behave, where if we have two hard surfaces colliding with one another, they're not going to rebound very much. They're not going to compress very much, they're not going to rebound very much. So the interaction time is very, very fast. Happens in an instant. Okay? Thus, the force is very large between the two surfaces. If instead we have a collision and the object is given time to deform and rebound, that extends the amount of time of the interaction, but it also reduces the force of impact. Okay? That's why anytime that we use cushioning, the cushioning will actually increase the time of the interaction, and that decreases the overall force. And again, you'd much rather be hit by something soft and cushy like that than a softball or a hard ball. We see this in safety equipment. How do we extend the time of collision? Well, we use soft cushioning, which will take time to compress, and that'll bring that force down because it extends the time of the interaction. These also have a hard outer shell, and that distributes the force over a larger area, and that decreases the local pressure. Okay? The skull, the ribs are very susceptible to fracture if the force is very concentrated in those areas. So we spread the force out, and we also reduce the time of the interaction by putting that cushioning there. It's a little bit difficult because you want as much cushion there as possible without affecting the performance of the athlete. In this case, a bike helmet is made to be streamlined, but it's made out of a hard foam, I should say, not so much a hard foam, but a rigid foam, which on impact will collapse once. Whereas the football equipment, hockey equipment, softball, baseball, protective equipment, all of these have materials that will absorb multiple blows. The bicycle helmet, being made out of material that permanently deforms, a styrofoam, should be replaced any time that there's a fall. And again, here you can see more padding that's used to extend the time of the interaction and decrease the force of the collision. In an automobile, surviving an automobile accident is much more likely today than it was in the past. In the past, the automobiles were very rigid, so during a collision, people weren't wearing seat belts. They just smash into the front of the dashboard or the steering wheel or the seat. And this rapid collision would, in many cases, kill them. So what we've done is we've devised a number of different systems that reduce the force by extending the time of impact. Airbags, seat belts, crumple zones built into the car, all of these extend the time of impact and make injury much, much less likely. The airbag is specifically made to deploy and then decrease in pressure very rapidly after it's deployed. Seatbelts prevent you from colliding with whatever's in front of you, okay? But they do have quite a bit of give. Consider this. A 75 kilogram person traveling at 27 miles per hour, 60 miles per hour. If they're in a car and they suddenly slam into a rigid structure, maybe a telephone pole, maybe a concrete wall, something that's going to stop them instantaneously. If it takes them only 1/100th of a second to stop, that corresponds to 280 Gs. They are dead, regardless of how fortunate, how strong they are. At 280 times the acceleration of gravity, in fact, anything over 100 times the acceleration of gravity, the pressure in your blood vessels becomes so high, your aorta will rupture, you'll have tremendous internal bleeding. Always fatal. Okay? So what we try to do is we try to decrease the acceleration, decrease the overall force of trauma that the body has by making the collision last longer. Sounds counterintuitive, but if you think about it, if the collision's over instantaneously, all that impulse is transferred instantaneously. If the collision takes time to evolve, then the impulse can be spread over time, so the force can be spread over time. So we need to keep the accelerations well below 100 Gs, and even at 25 Gs, we're going to experience some pretty serious injuries. So again, increase the time of the interaction. Let the body come forward a little bit, okay, but not far enough that it makes contact with what is in front. Now we can go from, maybe what is a hundredth of a second to 15 times longer, which is 1/15 as much force on the body. Doesn't still mean that you're not going to get hurt, but extending the interaction time greatly decreases your chances of injury. Airbags increase the time of the collision. They also absorb some of the energy, and again, prevent you from hitting what's in front of you. The most important thing, however, is to make sure that you're a safe distance from the airbag, because when it does deploy, it comes out at 200 miles per hour. Okay? So it quickly inflates. You don't want to be there when it inflates on you, and that's the reason why we don't want small children in the front seat. Airbags work with a crash sensor. This triggers a chemical propellant, not quite an explosion, but a rapid expansion that inflates the airbag. And again, sensors are all over the car. These sensors, if they detect more than about 2 Gs of acceleration, okay? You can't get your car to stop, in 2 Gs, and you can't get it to accelerate in 2 Gs, so the bags will not deploy for that. But more than 2 Gs for acceleration, maybe more than 2.5, the airbags will deploy and try to cushion the impact. Each airbag has these little propellant discs. They have an igniter where an electronic sensor from the computer, the control unit, instantly starts a reaction. The sodium azide breaks down and becomes nitrogen gas. The nitrogen gas inflates the bag, and wherever you have an airbag deployed, you've got one of these little chemical inflators there. Now, researchers have determined that the risk of zone for drivers' airbags is the first 2 to 3 inches. So you want to be at least 10 inches from your airbags. Set your seat so you're never closer than 10 inches from any type of airbag that can deploy. In race car driving, NASCAR, we actually have much higher speeds and therefore higher momentum. Famous drivers such as Adam Petty, Kenny Irwin, Tony Roper, and Dale Earnhardt Sr. were killed when their cars suddenly were pushed into the wall. Walls were, very hard, and what didn't seem like a very violent collision was enough to create very large accelerations in the person's neck. Now, we use the HANDS device now, which restrains the helmet and neck from going forward, and this prevents this type of injury. The way it works is this: you don't want to restrain the body other than at the 5 points where the seatbelt for these cars connect, because you want to be able to press the release very quickly and get out of that car if it's on fire. With the HANDS device, it doesn't restrain the helmet to the car or to the seat. It restrains the helmet to the body. There is a carbon fiber mold which has a little seat of its own back here, and 2 tethers that allow the head to move a little bit, but not far enough to fracture the base of the skull. So the problem that they were having here is the last vertebrae right before the skull, or the first vertebrae right after the skull, was fracturing due to a very violent snap forward. And by putting these tethers right here, prevented the head from going too far, from hyperextending, or I should say in this case it's a hyperflexion, and creating this type of fatal injury. Okay?